Good morning, all of you. I'm Libu Manjakkal, working as a research associate in University of Glasgow. I'm working mainly in the area of electrochemical technology such as sensors and supercapacitors. Today, I would like to discuss with you one of our recent work related to graphite polyurethane composite based supercapacitor. In this work, we prepared a composite, graphite polyurethane composite, and printed on the top of a graphene sheet. And this electrode used as a wristband based supercapacitor for a wearable electronics application. Before going in detail about the performance of the supercapacitor, why we need a wearable energy system? You know that recently there is a tremendous increase of various type of wearable sensors for sweat monitoring or a wound monitoring and various applications. This include physical sensors, chemical sensors, and biological sensors. And and in addition to this, these sensors require a readout electronic circuit or a data transmission circuit, and this required again an electronics component to operate. And in addition with these sensors and these sensors for wearable, there are different type of sensors also used for human machine interaction like strain sensors, touch sensors, and pressure sensors. All these sensors and related electronics components required power to operate. You can see here there are different multi sensors used for sweat monitoring and also a stretchable pH sensors with a stretchable antenna and a related electronics component for online monitoring of our sweat pH value. And there is a strain sensor which is used for a human machine interaction. And also in our group recently a temperature and strain sensor integrated with a smart bandage used for online monitoring of a wound for a wound monitoring application. All these sensors or the related components working in the operating power range of nanowatt to microwatt power. So, uh, for to operate these sensors, until now, different type of energy systems are used. For example, there are various energy generators or harvesters. This include biofuel cells, thermal energy, and also various mechanical energy like triboelectric, piezoelectric, and the major solar cell like flexible. There are different type of flexible solar cell are used for to operate these sensors. This energy generated the generated energy from these devices are stored in different type of energy storage like lithium ion batteries or supercapacitors. There are different type of material used for lithium ion batteries or supercapacitors. In addition with these energy generators and energy storage devices used for powering, there are self-powered electronic skin or self-powered sensors are also reported. For example, a piezoelectric or a triboelectric nanogenerators itself act as a sensor and an energy generator. In our work, one of our work, we used solar cell as a energy generator and directly used or directly integrated on top of a touch sensor to operate the electronics component of the touch sensor. Among these, one of the critical component is energy storage because if we need a continuous operation of a sensors, a suitable energy storage device is required. Among various energy storage devices, batteries have very high energy density. For example, different type of high energy density batteries are there, like zinc air battery, lithium ion battery, lithium sulfur battery, and which store huge amount of energy for a long term application. But the problem of such a battery is that it generates temperature and which may be not good for a wearable application, especially for a skin. And also the charging time for such a battery is more than 1 hour to get a full charge, and some of them are not flexible also. And moreover, these batteries are life cycle is very low and almost 10 raised to 3 cycles. Uh, to overcome this issue, there are recently major work is going on in different type of supercapacitors. Supercapacitors can produce very high power as compared to battery, but the energy density of the supercapacitor is low. So various materials are now utilizing for to improve the energy density of the supercapacitors. The major advantage of a supercapacitor is it have a very high flexibility and stretchability, and charging time is less than 1 minute, and it have a life cycle of more than 10 days to 6 charging discharging cycle. And as compared to battery, the material, less toxic materials are used for supercapacitors fabrication, and it is easy to integrate with various energy generators because of the very quick charging time. Recently, many of this work is going on how to improve the energy density of a supercapacitor, and especially for a wearable application. So the one of the important point when we need to consider in a wearable application is that the electrode need to be flexible. So the material preparation need to be low temperature processing. In this aspect, what we done is that we synthesized a new material called graphite polyurethane composite. Graphite have a very high electrochemical using for a electrochemical double layer supercapacitor fabrication. In here, polyurethane acts as a very good binder in a low temperature process for a graphite composite. As reported in this previous work, here the fabrication is almost similar, where we used a PET or a PVC as a substrate, and on the top of a substrate by graphene sheet, it's a multi-layer graphene sheet, it's a commercial electrode. We use it as a current collector and bonded on the top of this substrate, and then the graphite polyurethane is printed. And then here is there is one side we attached electrode and insulated with the polymer. And then here we used the phosphoric acid as an electrolyte for the supercapacitor. And there are two types of such electrode. We made such electrode, and then polyester, cellulose polyester used as a separator for the supercapacitor fabrication. The advantage of cellulose polyester is that it holds the wettability for a long time due to the absorption capacity of the cellulose for the liquid. Here you can see the cross section of the electrode, and then the major advantage of this graphite polyurethane composite is that its surface, because to improve the performance of the electrochemical performance of the supercapacitor, the surface of the electrode need to be more in very good interaction with the electrolyte. Here you can see that we are measured the contact angle for a graphene sheet and compared with the graphite polyurethane. The graphene sheet shows more hydrophobic character. In a supercapacitor performance, we need this electrolyte need to be properly distributed around the surface. So as compared to graphene sheet, you can see here graphite polyurethane composite in the electrolyte is more distributed. And then the reason behind this is that the graphite polyurethane we analyzed through scanning electron microscopic image. The surface of the electrode, it have a rough surface and with the microflakes distributed around the top. And here you can see the cross section of the graphene sheet and polyurethane composite. We further studied the crystalline properties of the material through XRD and Raman spectroscopic analysis. You can see here that in XRD the peak is more towards the carbon graphene sheet, and it is more similar to the carbon. And also in a Raman spectroscopic, mainly G and 2D bands, it is more related to the graphene, and peaks are observed. And due to a small peak here in we observed that it is due to the structural defect of the material, composite material. And further, such a two electrode we fabricated this electrode and applied when we applied a potential in the mechanism, when we applied the potential between these two electrode, you can see that here there is a GPU film, graphene polyurethane film is there, graphene sheet is there, and we depends on the polarity of the applied voltage, the ions from the phosphoric acid, it contain H plus and PO3 4 minus or different negative ions, and depends on the polarity of the electrodes, the ions are distributed. For example, towards the negative electrode, when we before charging, the ions are distributed all around the separator, and once we charging the device towards the negative electrode, positive ions are attracted through electrochemical double layer formation, and you can see here that the ions are distributed around the surface of the electrode. Then we characterized the electrochemical performance of this device. You can see here that in impedance spectroscopic analysis and the Nikias plot, the equivalent resistance of these devices in the 2 ohm. It's a very low resistance and almost a Warburg impedance you can see here, and a phase angle around minus 70 degree through the board plot you can see. And in a CV analysis we observed almost a rectangular shape, and it is similar to the electrochemical double layer formation and of the supercapacitor, and characterized the CV for a different scanning rate from 25 to 200. You can see here that the peak current, a straight line, almost a straight line, it is due to the diffusion of ions. And further we characterized the galvanostatic charging discharging analysis, and for a different applied current. And you can see here that the potential of the with increasing the current and the potential, there is a saturation potential. We measured the saturation potential of the device for a different current density. We also, in previous work, we also reported the various the different long charging discharging. You can see here the for a 10,000 cycle, we characterized the charging discharging for a device, and the first 10 cycle and the last 10 cycle. And here you can see the initial cycle and the final cycle almost similar properties. That means that this supercapacitor shows a very good performance even after 10,000 charging discharging cycle, even 1 milliampere current. And also characterized without bending and with bending. Different bending radius have influence on the supercapacitor, and here you can see the cyclic bending performance of the device as well. Finally, we applied this device on a as a wristband supercapacitor into power and LED. This device shows an energy, is a capacitance, serial capacitance of 5.38 millifarad per centimeter square in the energy density of 3.7 microwatt per centimeter square and 1.15 milliwatt centimeter square. And our next plan is integrate this with different type of physical sensors and energy generators. And thank you for the support from our best group. Here you can see, and the funding agency and EPSRC. Thank you so much. If you have any clarification required, you can contact us. And here is our group website also. Thank you so much.